All right, so we went over the slides. Go ahead and hit in here. So Jupyter, hopefully you guys all got that installed up and running. If you didn't, the commands are in the chat. You'll need to pip install Jupyter Lab and then run Jupyter Lab using that command there. If you are having issues, let me know. There is another command you can run if Jupyter Lab is giving you issues. Blake knows all about that, don't you, Blake?
Oh yeah, that was so pretty rough yesterday.
All right, so TensorFlow and PyTorch. So TensorFlow, first one that was able to come to market. Google led it, and it was very powerful. Still is very powerful, but not user friendly. There was a module called Keras, which was a wrapper around TensorFlow to make it actually usable to individuals like you and me who wanted to use it. It was so good, in fact, that Google ended up consuming Keras and adding it natively into TensorFlow because using base TensorFlow was pretty cancerous. So usually, whenever you do anything in TensorFlow, you're going to be using it through Keras because you don't want to do it through native TensorFlow because it's cancer. Due to this cancer, Facebook got in the game and said we can do it better, and they did it better. They did it a lot better, and people use their stuff a lot more. The big issue with TensorFlow originally is it functioned a lot like the underlying C code because there was a lot of one-to-one relationships. So giving some PhD math person that only knows R and some Python and telling them to program like their C dev is a no-go. So people fled and used Torch. So we'll go through the TensorFlow example here first. Mostly because I grabbed this from online. I have not ran this one, so I have no clue if it works or not. So I'm going to go through formatting now for Jupyter Lab. So Jupyter Lab, you can have these items, these little blocks. And like I said, they save states. We're going to make a couple here above our code. And this code I grabbed from, actually, it's running in here. We're going to be using this one. This TensorFlow here. So I'll go ahead and put this link into here. That should be able to open it up on your guys' own systems. So as you can see, things are segmented off, and you can add these text blocks if you would like inside of your Jupyter Notebook. And it's just markup. So if I go inside of Jupyter here and I add some markup like hello world and press play, I think I messed it up. I'm supposed to make it as a markdown block, and I can click that, and then you can look at my glorious misspelling, and that's how you can add nice little text blocks in it. So that's what they're doing here in Google Colab. Some of the stuff they use in the Google Colabs do not work in Jupyter Labs. I'll point that out if I see any items here. It does not look like there are any. When you are using Jupyter Labs, you need to run this command %matplotlib inline in order to get the matplotlib graphics to print inside of this platform, or if you're using Jupyter Lab. So we'll go ahead and go through here. First thing is installing TensorFlow 2.7. So we'll go ahead and do that, and we just click the play button, and we'll start doing that automatically. You can also go ahead and click through more of these, and it will just queue up these items. I'm not sure why we're downloading the quantum library. I guess we'll figure out here soon. Okay, this is using quantum neural nets. Okay, this might not be the example we want to use then. Let's go back to this guy. So we got this raw code here. We need to convert it into a proper notebook format. So we'll go ahead and grab the import statements and put those all into one guy and go ahead and run import on that. It's probably going to error out because we're missing sklearn, and I believe we're missing TensorFlow. So we can make a new block, move it in front of everything, and if you do the exclamation mark, you can run commands on the underlying terminal. So if we do exclamation mark pip install sklearn, press play, that will install sklearn onto our box. So it's just taking a second to think, but you should see outputs here in the pip install to start running. This whole thing runs inside a web browser, correct? Everything runs inside for Jupyter Notebook, you launch it via the terminal and everything runs in a web browser. So you can see this downloaded and installed. So let's rerun this. Probably going to error out on TensorFlow because I'm pretty sure I don't have TensorFlow installed on my computer. But we'll see here in a second. And what do you know? TensorFlow is missing. Now, I have the great privilege of using TensorFlow GPU, hopefully. TensorFlow GPU install. The other big cancer thing with TensorFlow is the GPU installation of it used to be super cancer. Now it's not as much cancerous. That's why people use PyTorch also, because it just worked. But TensorFlow has a pretty cancerous setup, and it looks like they still might. I'll just go ahead and copy this, and hopefully worst case scenario, we'll just use the CPU, because TensorFlow is pretty cancerous. And if Wade was in here, he would tell you it's pretty cancerous also. All right, looks like that installed? Question mark? That was really quick. I am, hold on. I don't trust this thing.
Your last error there is Python 3 was not found.
Okay, yeah. So that should be installing it now. So has the asterisk. Asterisk means it's getting processed. If for some reason you want to restart your entire notebook from a clean terminal, you can click this right here to restart your kernel. Additionally, if you have different versions of Python installed, you can load up different kernels. So this is going ham. Usually it has like the loading bars being printed out. I'm not quite sure why it's not doing that right now. Kind of like how it had the loading bars here getting printed out. This is how it should look. So while it's doing that, Google Colab is a free resource. So whether you want to actually look through this quantum example, it's up to you. But if you just want to make a new one, you can just make a new notebook right here and utilize their GPU or TPU resources out of the box. And you can follow along this way if you don't want to set up Jupyter Notebook or if it's being too much a pain, and everything gets synced to your Google Drive. So all of these will show up inside of your Google Drive in your Google account. All right, this guy is still taking its sweet, sweet time. Any questions so far? Well, there we go. So the output may be a little bit cancerous and maybe you don't want it to linger around. So if you right click on the output, you can clear this specific output or clear out all outputs. We're just going to clear this specific output so we don't see it anymore. I'm going to run this guy here down below. This should import everything once so we don't, as you can see, importing TensorFlow or PyTorch will take a while. It's a lot of stuff that's being loaded up in memory. So this alone will increase your productivity by a lot because you no longer have to run this block of code over and over again in order just to run one machine learning session. You can just do it once and then program out with it just being in memory. It's kind of similar to if you are used to, let me pull up a new terminal here. If you launch, God, what is, okay, don't do this to me. If you load up a terminal and you just type in Python and get that IDE session or the interpreter session going on, it's pretty similar in the sense of like this, where you can set a variable and it's like saved so you can refer it later on. Kind of similar to what's going on. So this all imported successfully. We have the number 8 here showing up, which just means that it completed. This was the eighth thing that we ran and it completed. So now we have access to all of these guys and we don't need to rerun this block again. So on the next block, we'll go ahead and create all of these functions. You could put all these functions on their own block. Well, actually, we'll go ahead and do that. We'll put each function on their new block, so that way if we want to alter one of the functions, we don't need to alter or rerun the entire block. We just need to alter that one specific function. So we'll go ahead and do plus here and delete this. Copy this. Delete. Copy this. What have I done? Oh, this went down here below. Here. Copy this. New. Almost done. Copy this. New. Delete. And copy this. And then we'll just have our run function here. Again, asterisk, the TensorFlow example I have not ran. I've only ran the PyTorch one. So we'll see if this works out of the box. So now we can just click play and load up all of these functions. And just every time you click play, it will go down to the next item. And it looks like they all imported successfully. So let's go ahead and run this bad boy and see if it will actually run and work. Or if it will error out and die miserably. So it looks like it's running. Let's see our resources here. It's actually using... God, why is Discord using so much GPU? Doesn't look like it's using any GPU resources, so it might be running on CPU only. We'll check back here in a second. All right, so let's go through this a little bit. First is loading the data set. So we're getting the default MNIST data set, and the MNIST data set is an infamous data set for the Hello World, typical Hello World program in regards to machine learning. It's just a bunch of, I think, 16 by 16 or 32 by 32 photos of hand-drawn characters like this. This is what the data set is comprised of. And basically what you're doing is character recognition. So you're getting fed these single photo numbers, and the machine learning model is going to learn how to recognize each one of these. So this will not be able to handle out of the box entire strings of numbers. It's only training on every individual character, which means that if you want it to read entire strings of characters, you're going to have to make another machine learning model that can recognize strings of characters and then cut that up into its individual characters, and then this guy can run afterwards. That's the biggest confusion that people have, is they think there's just one machine learning model that you train that does everything. No. Machine learning models in production are usually several different machine learning models that are all stitched together to create a pipeline to process data. For example, extracting faces from photos. It's a several step process. Typically what you will do is, first, there will be a model that just purely identifies if there is a human in the photo. And if there is a human in the photo, there may be another process that actually draws the bounding boxes for the single human or multiple humans in that photo. Then those humans will be extracted out, and then there will be another process, another machine learning model that will then identify the face and extract the face, and maybe it also identifies other features that are in the photo. But it's a multi-step process. It's not just, hey, I'm going to feed raw photos of anything and it's going to then output faces. That's not how it works. You gotta break it down to its core components. Okay, so it looks like it's running and we're getting 98% accuracy right now. This is a pretty dumb output. This is not informational at all. So I'm going to run through this real quick, and we'll switch over to PyTorch here while this runs, because it's not good for example wise. But loading the data set. This lets us load the entire MNIST data set from from MNIST, which is being imported from Keras datasets. So a lot of these machine learning libraries have datasets that you can just grab that are pre-built into them. And I'm talking like terabytes large data sets you can get from some of these things. So there's more than enough data and it's already labeled, so you don't need to do any of the cancering label work yourself. So we're splitting up this data set into two distinct parts, the training set and the testing set. It's already split up inside of the MNIST, so you can just simply run this to split it up in its two types. If you were doing this manually, you would have to do this more manually. When you're training a machine learning model, you must have two types of data sets. You must have the train and the test. The train is what you will be training the machine learning model on, and the test will be new data it's never seen before in order to test how accurate it is. Because there are issues that can show up in machine learning where you're over-tuning or under-tuning your model, which means over-tuning means it's trained too well on the training data set, so it only really recognizes the training data set and it sucks on other data that it's never seen before. And then under-tuning it is it just sucks all around. It doesn't work well on the training data set. It doesn't work well on the testing data set. You'll also notice there's an X and a Y. This is obviously crappy and uninformative to a random viewer like you on what it is. But the X is your raw data. So these would be your photos. And the Y will be the answers to that photo. So if a photo is a picture of the number 9, the Y will just say the number 9. These are going to be arrays. Each one of these are going to be arrays. And one will be an array of the data, and this will be just the answers. Same thing here in test X and test Y. This is the data, and this is the answer to the data. Because this is a supervised machine learning model, which means you must have the raw data and the answers to that data. There's some pre-processing that you have to do before, before utilizing a machine learning model. So we're reshaping the arrays right here in order to make sure they are 28 by 28 by 1 photos. So 28 by 28 in their grayscale. So it's reshaping. They might have already been in this state, but this is just to confirm that they are in a state that we want. It is easier to train on grayscale photos that are only varying between 0 and 255 in their value compared to RGB photos, because that's now 3 dimensions that you need to compute on instead of just 1. And this is getting the categorical data. So basically, if you were doing machine learning models only work on numbers. So if you had words that you were associating with photos, you will need to basically associate those words with some type of number value. So that way, you know, if it outputs the number 10, maybe that's the key for a human. You do not train on anything but numbers. So that's a part of the pre-processing step for machine learning algorithms, is you need to format the data and then extract out any text and make a key for that text data, and then use the key in regards to your the values you pass it. So this is just loading up the data set, doing some pre-processing, and returning it. This is doing some preps on the pixels, so it's just making sure that everything is a float 32 value instead of whatever it might have been before. This is a NumPy specific. Is this the NumPy? Yeah, this is a NumPy specific item. So NumPy is a fast way of doing array computation because a lot of it is optimized in the C below. It's way faster and way more intensive than the normal Python libraries for arrays. So this will force everything to be a float 32 under the hood. And then this is normalizing it. So again, your data not only has to be just numbers, but it needs to be normalized so all numbers are between 0 and 1. You can't just feed it data that's 0 to infinite. It doesn't know what the upper and lower bounds are. So here you can see we have grayscale photos. So there's only one dimension, and that dimension can only be 0 to 255. So you can see here there's everything is converted to floats. So these were probably integer values before because it was 0 to 255 in your photo. Makes sense. They're making it into floating point values. And after that, they're then dividing it by 255, since that is the max value you can have on a grayscale photo, to normalize it between a range of 0 and 1. So that way, the machine learning model knows by default 0 and 1 is its upper and lower bounds, so it will give you a result between both of these numbers. So next is making your actual machine learning model. You can see here, this is the whole shebang right here. These couple lines of code. As you can see, there's lots of code that isn't for that, because like I've said in the presentation, most of your time is not making the machine learning model. Most of it is prepping data and doing everything around the data in order to make sure it trains properly. But the model itself is really easy and short to shit out. So there's several different ways or different models that you can use. Let me see if we can Google real quick. ML different neural networks. Let's go ahead and look at some of these different neural networks that exist. Well, is this one? No, let me see here. Might have to say neural network types. ML neural network types. So here we go. So there's only a couple base neural network types. So this one is boasting there's 6 different versions. Let's see here. There's the default neural network. So these ones are very simple, where data is computed. These are called ANNs, usually artificial neural networks. And this is just pretty straightforward. You feed it some type of value, and the value is computed and moved along down the neural network. It's the most basic form. Then there are RBFs, which I am actually not quite sure what RBFs do. What the hell? There we go. There's RNNs, which are recurrent neural networks, which basically, instead of moving down just in a straight line, there's mechanisms in place in the nodes that will feed the data backwards and back into itself. You do not need to program this yourself. All you need to know is it exists, and you basically specify it right here. So con2D is for 2D images, and this is for doing a CNN. If you wanted to do an RNN, there's things called LSTM, and it's as simple as just doing that, and all the math is already done for you. You just need to know what type you require. This is for any RNN is specifically in regards to memorizing some type of output for further on reference. So for example, if you're processing text, you need to know the context of previous text you've analyzed and read in order to make an accurate assumption of what the next word should be. Additionally, this may come into play if you're doing prediction of weather or something. You may need to know what the last couple steps of your weather patterns were in order to make a proper prediction later on. So that's what RNNs are good for, is looking at previous data you've seen and making a new assumption on data moving forward. CNNs are convolutional neural networks. These are used for image recognition, pattern recognition, any type of recognition. These are great for it. What they do is they generate these filters. So this is a 3x3 filter right here that is jumping every 2, you can see in the graphic, it's moving and jumping every 2 pixels and analyzing for specific patterns that it's trying to recognize. So this is great for doing photo recognition, which is what we're using. We're using a convolutional neural network that is a 3x3 grid, and that 3x3 grid will go through our entire photo looking for patterns in its shape. And there's module neural networks. I've not used these ones either. God, I'm blanking on the other big one right now. But regardless, we're going to move forward. We're using a CNN. So this is us declaring that we're going to be using a sequential model. So this is just starting it out. I'm not quite sure right now what the sequential is in reference to. I promise I do this for my job, but it just shows you don't need to know all this mathy stuff in order to utilize it. I'll show you more when we get to PyTorch, and then when we get to the Hugging Face examples on how easy it is now. This is kind of how it used to be. So we're using a convolutional neural network, and on this you need to choose. So traditionally when you traverse a graph, it's just add up the values as you move along, and then that's your output. Instead, we don't want to just do adding up the values, so we can change the activation function, which is basically how we compute the values along the graph, and we're going to make it into the ReLU. Basically, ReLU is used for most of the machine learning models. You can just use that and get by with most of it. Also, good luck Googling a lot of stuff. A lot of this, like, I'm not shitting you, a lot of this is random guessing. A lot of it is random guessing in the machine learning world. The PhDs kind of make educated guesses, but they are still random guesses for the most part on what will work and what doesn't work. Kernel initializer isn't really required, and I'm not sure what it is. And then input shape is the shape of the data that you're going to input. So this is important. This goes for all machine learning items. So whether you're using the AI aimbot or you're making something yourself, the input shape is hard-coded and something you always have to adhere to. So if you make a machine learning model that can only read grayscale 28 by 28 photos, it can only ever read those type of photos. It cannot read bigger photos or smaller photos. So before, let's say you take a photo of a character that you wrote on a piece of paper with your phone. It's probably going to be several megapixels large. You need to pre-process that photo, aka shrink it down so it is a 28 by 28 photo. Whether that's cropping it or straight up resizing it, you have to resize it by 28 by 28 before you run it through this guy, period, or else it will not work. That's what the AI aimbot is doing behind the scenes automatically for you, is every screenshot that's taken, it is readjusting and resizing that photo to fit whatever the input shape of the machine learning model is. So be aware of this, especially it's pretty common if you're taking photos like we are with the machine learning aimbot. It will take RGB values, but sometimes your photos will have RGBA values, so they'll have the alpha column. You need to drop the alpha column in order for it to be compatible with the machine learning model. Next is doing pooling and flattening. Pooling is basically making the image even smaller, so it's taking the 2x2 items and it's making it into one item. So every 2x2 pixel grid is becoming 1 pixel. Flatten makes this from a 28 by 28 array into one single long array. A dense neural network is just the default neural network that I showed you guys up at the top. So this one, the very simple one, and there's 2 layers. One has 100 neurons, so that's 100 of those circles large. The next one is 10. So let me pull up Paint here real quick so we can kind of draw this out so it makes visual sense here, because pictures are good. So we have a neural network that takes a photo, and those photos will be in a 28 by 28 large grid. And the convolutional network will look for patterns in that photo. After looking for patterns in that photo, it's going to be reduced in size to whatever 2x2 divided by the 28 is. So it's shrinking every 2x2 grid into a smaller photo. After shrinking into a smaller photo, it still has the 3-dimensional or 2-dimensional size. It's being flattened into one long array essentially of data values. And then after being flattened to this long array of data values, it's being fed into a 100 long neural network, and these will, connect however they will connect. It is a dense, so that means every single node is connected to every other single node on the network. So if there's 100 nodes on this next neural network, all the pixel values will have, each one of them will have 100 connections connecting to every single node on this. Then after that, there are 10 neurons, and it's a dense network, which means every single one of these 100 neurons here are connected to every single one of the 10 neurons over here. Basically, it's simplifying it. So what's going on here is it's guessing. We're doing this pattern recognition, which is 3 by 3, which is pretty common for a convolutional network, is 3 by 3 grid for recognition. After the recognition, it's going to this dense network. This 100 was an arbitrarily chosen number. It could be more, it could be less, but not too much less. You wouldn't want to go less than the 10. Usually this number is determined based off of how many items are left over after the max pooling, which there are ways to print out how many items were in here. This last guy is a 10. Why is it a 10? Because we're analyzing numbers between 0 and 1. So this is the output of our neural network. This will tell us, depending on which node is lit up, it will be between a 0 and 10 potentially, and that will tell us whether our number is a 0, 1, 2, 3, 4, 5, so forth, 9. It's 0 to 9. So there's 10 digits. And this softmax is usually the activation function you will use when you're doing your outputs node. But this is your whole model right here. There's only 3 these are the only 3 like big nodes in the neuron picture. So if I go over here, this picture, there's only 3 layers of this. These 2 are kind of just functions that get applied to do some simplification of the data. But it's only a 3 large neural network. So this can set the learning rate. So basically, if your machine learning model was wrong, how much do you want to punish it, or how much do you want to reward it? So this is how much it will change the value every single time if it is wrong or correct inside of these neurons. You can make this a lot less. You can make this a lot more if you want. It's completely up to you. And this will have effects on if maybe your machine learning model is set too high, and you know that because your machine learning model is making too many assumptions too quickly. So you should maybe make this smaller so it more thoroughly examines the data before being rewarded or punished with a large reward. And this basically just compiles your model together. So like I said, this is kind of C underlying. So these are like individual C items, and the compile will smash them all together in the back end. So they're very much optimized and ready to go. And we're going based off the metric accuracy. Where does the accuracy come from? Well, you have to read through the API. There's a lot of stuff in the API that will tell you. So it might be a little overwhelming. And trust me, you don't have to do this stuff if you're going to be a machine learning person, at least off the bat. You'll learn about it as you go forward. But I promise you, there's only a handful of these items you can choose from, dense and conv 2D. There's only a handful of them. So once you learn them, you know them, and it's not as overwhelming. Also, activation, there's only a handful, I think like 3 to 5 default activations. You pretty much always default to ReLU, except for your last one, which is usually always softmax. And your learning rate is just usually some type of 0.001 item. Seems like a lot initially, but I promise you, it's if you hunker down for a little bit, it's not too much. So this is for doing evaluation of the model. So lots of mathy stuff for you automatically, like k-folds to shuffle the data together so it's not the same basic array that's being fed to it every single time in the same fashion. This will help shuffle the data together like it's a card deck before giving it to the model, so you get a more accurate train. Is this doing... Okay, well, I don't know why this says evaluate, because this is doing training. So right here, fit is how you train your model. So that's where you're going to give it the training data. Epochs is how many times you want it to go through your data. So 10 times. Batch size is how many images you want it to analyze at the same time, which is 32. This is a memory intensive process. So the higher this number is, the faster you'll compute, but the more memory you'll use. So pay attention to your memory, because you don't want to use too large of a batch size where your computer will crash. Machine learning is extremely unstable for your computer, and your computer is has a high probability of crashing or being very weird if you are doing machine learning on it. Next, we're going to evaluate on our test data set. Like I said before, it's never seen before, and this will just tell us what the current accuracy is. If we scroll down here, look at that, we got the output. So we'll look here in a second. Summary diagnosis is the graphs of its training. We'll see that here in a second. This is just printing a print statement and then some showing off the plots. Test harness. This is just basically our main. So loading the data set, normalizing the data, training the model, and then output of the model stuff. So if we look right here, our accuracy was hovering around 98% the entire time. You can see here our learning accuracy rate over time as it was going up. So the blue line is the one we want to look at here. And we were getting more accurate and closer. I think the blue line is the training data set, so the stuff that it kept seeing over and over again. And the orange is the stuff it never saw again, the testing data set. So this is how you utilize this to indicate whether your data is getting too over-tuned to your training data set, or you're testing or under-tuned, so it's not doing well on either of them. Standard deviation, so this is over time. What was the upper and lower bounds of what was your accuracy and what was the typical average, and then the line is your actual mean for accuracy. So some cool stuff. There's a lot of visuals that can help you. What questions do we have here? This is for TensorFlow. We're going to go over PyTorch, where we're going to be a little more safe and not in scary territory. No questions? As you can see, this is probably the most mathy shit you've ever seen in programming, because it is kind of mathy. But I promise you, there's only a couple things you need to mess with. So here's the PyTorch example. It's a lot smaller. Let's go ahead and break this out. So let's take these guys here and put them in the first block and go in and import that. Please update Jupyter. Progress not found. Well, hopefully that doesn't run into any issues for us. Next is all of the items that we can edit. So we'll go ahead and grab that and put them up front. Next will be our downloading of our data set and normalizing the data. So we'll put that there. Next will be our convolutional neural network. So we'll go ahead and grab that. I'm going to clear this. And next will be the pre stuff. I guess we could just keep this here because this is all basically the main. No. We're going to take everything that's in the training and put in its own block. And then this is for testing and saving. We'll put that in its own block. and then this is for outputting the answer. So as you can see, this is a lot simpler and a lot scarier, a lot less scary looking. So at the very beginning, we have number of epochs. So this is the time, how many times we want to train on our data. How many different items we have in our data. Well, we're recognizing characters between 0 and 9. So there's 10 different items we can recognize. Batch size, so how much we want to calculate at the same time. And then our learning rate, so how much we want to reward or punish it for being wrong or correct. And then this is just some stuff for getting the data, which we don't need to mess with because we're downloading it. So here we are doing a transforms to apply to the data. So I guess we're getting our transforms ready for normalizing the data. I'm not quite sure why it's formatted like this, but most important part is here we're downloading our data set, and after we're done downloading our data set, we're then transforming it so it's all normalized. So we'll go ahead and run that. This is our convolutional neural network, which is a lot simpler to look at than the TensorFlow one. So again, we're looking right here. We are making a neural network that's sequential. So I believe this means feed forward only, but it's convolutional 2D again. And this is going to stride and padding is talking about the how many pixels it moves across. So it's moving over 1 pixel across each time it analyzes and looks for patterns. It's using that rel-u activation function that you saw earlier. It's just formatted a different way here. And afterwards, it's doing the pooling. This is all in the same one layer. Then after that, we're doing a second pass in a second layer with another convolutional 2 network using rel-u again, and then pooling, so making everything smaller. Then after that, we're doing a dropout, which the dropout will remove connections that aren't really necessary. And then fully connected is the neural network we talked about. So this is 1,000 nodes large, and this one is so this calculation is basically the calculation of how big this guy is. So how many filters you have at the end of that, and it's filtering it down to 1,000 just normal neural networks that are fully connected, and this is bringing it to our final 10. So there are 4 layers in this. So if we look here, this is us building it. So we're defining things here, and then this is actually us building it out. So layer 1 is going to be this layer, and that's taking in the initial data. Then layer 2 is feeding in the output of the previous layer into the new layer, and then this is going to be reshaped a little bit, so that way it's ready for the dropout. So it's reshaping it into one singular long array. So it's just one. It's just a 1 by whatever long array, so no longer 2 dimensions. This will get rid of items that are no longer needed, and then this will fully connect it twice. So once is the 1,000, and then the second is our final output, which is the 10 items. So once we have this, it's as simple as saying this to generate our model, and then this is going to be our loss function and optimizer. Loss function is the how much each item will, I believe, be punished by, or it will, I'm kind of fuzzy on it right now. I believe it's how much it will be punished by, and then optimization is for, in regards to learning rate, so how much it will be awarded. So training is just in a for loop where we get all the data, and we train it by just doing this. And by doing this, it learns, and then we step it forward and keep repeating this. And this will also output us, while it learns, a nice output of, you know, what step it's on, how well it's doing, accuracy, and so forth. So if we press on to that, you can see we're already now training, and this should be on my GPU. It doesn't look like it is using my GPU because it would be underneath PowerShell because it's using PowerShell in the backend. But you can see we're chugging along right now. We're on, the first iteration through everything. There's 600 photos that we're analyzing right now, and we've analyzed 300 of them so far through our first run through everything. This is our current loss and our current accuracy. So we're pretty accurate. We don't need to retrain this 5 times. So I'm going to stop this and go all the way up to the top here where it says number of epochs. I'm going to change that just to a 1 because we don't need to go over everything 5 times because we're already getting a very high accuracy rate. I'm going to run this block. I don't need to run the rest of the code. And I can go back down here and just rerun this. And now we'll go ahead and restart training. So while that's training, what questions do you guys have? This is still doing stuff rather manually. I'm going to show you after this where we are actually in the real world and how unmanual things are now. And how easy it is to actually do machine learning without having to do these minor steps. Questions?
I got a question for you.
What's up?
So in the real world, how does this stuff scale? Because right now you got 600 images. It's taking like a minute
Yes.
to train. How does that scale when we say 10,000 to a million? Like, is it linear or does it get like
Linear.
exponential?
Linear
Okay.
based off your hardware. It's literally just straight up linear. So you need to use GPUs. So it's kind of cancerous to scale machine learning model training. It's only now becoming practical and realistic for you to do it yourself. Because before you had to literally do a bunch of crap. Now PyTorch has a distributed learning module, but it's still a pain in the ass to use. It allows a lot of configuration. NVIDIA actually has some libraries that allow for very easy distributed workloads, but it's going to always take a lot of time. So if you go to the Hugging Face website right now, they are currently, it might have finished training early, but they were training their own model and you could watch it live. I think they replaced it with Dolly Mini. Oh yeah, so this is the thing where you can generate photos like cat playing the organ. Or how do you, what? Okay, we're gonna do guitar. Too much traffic. Okay, well, you guys might have seen these photos and memes and stuff. This is where it's generated from. And we'll show you guys how to use these machine learning models yourself off the bat. So let me Google Hugging Face training live session. God, of course it goes away. I thought they had a month left on training. NLP model. Okay, well they had a live progress bar here showing a model they were training, and literally they launched it. It's an NLP model, so mimicking OpenAI and stuff, or the one that you just saw the Google article on, and it was going to take 3 months for it to finish, and they were doing it on a supercomputer, and it's linear. So the more computers you have, it will literally grow in the amount of time it will take to finish computing. So this is taking a while. Hopefully we can download this on my computer and I can just run this for you guys locally. So this finished training because it's got to 600 to 600 and we only needed one time through it. So we can evaluate the model again here. We should get a similar accuracy rate because this should have been calculating accuracy based off of the training set, which doesn't look like it really was. So now we don't need to rerun this in order to just run this block of code. This is the magic of using the Jupyter Notebook. And we can rerun this any amount of time, and we don't have to retrain our model, which takes forever. And if we want to edit some code in here, we can just freely edit the code in here without having to change this stuff. So tested it on 10,000 different photos that it should have never seen before, and it got a 98.6 or 0.7% accuracy. So it's pretty accurate. And if we print this out, so I need to install Boken. So we'll go up to the very top here, make another guy at the very top for doing a pip install Boken. Cannot find, did I spell it right? I don't think I did. So as you can see, you can compute these blocks in whatever order you want. It doesn't matter. All that matters is the index number that you computed it. So even though I messed up and didn't have this module installed here at the end, doesn't matter. All this stuff is going to stay in memory and stay unchanged. And so I can do stuff like pip install and then fix the error down here, and I don't need to rerun everything. So here we go. We got our output. I don't know why this didn't print it in line. I'm guessing because I need that item that is in here that I told you guys you would need. Matplotlib inline. So let me put this right here. Nope, still doing it on a new. So right here, you can see the training accuracy of the model over time. And usually this is what you want to see. This is a pretty dramatic graph. But usually when you're training your models, you'll usually see if this is your graph and this is 0 and 100%, it will usually train like this. And kind of hover here around the 100% mark. Now you can guess on how many epochs you need, like what we kind of did, and change that up as needed. Or there's these things, there's another function you can use to automatically cancel training if things kind of stagnate, which is ideal, especially if you're doing machine learning on something massive, like probably what Hugging Face was doing. I'm guessing that's why it ended early, is they had 3 months, but it looks like it stopped earlier because I'm guessing it started to level out, and their whatever function they had saw that was leveling out and said, okay, we're good here, boss. You don't need to keep training anymore. And it would end the training earlier. So this is a way where you can visually see like what's going on. There's a lot of tools that are pre-built in that allow you to visually see what's going on. And we have saved off our model right here. So now our model is in this checkpoint PT file. So I can now give this to you, and instead of you having to retrain this yourself, you can just take this guy and load it up, and you can use my model. And right here you can see the MNIST data set we were using. What questions do you guys have there before we show off some Hugging Face stuff and how much easier it is? We went from super hard and mathy to less hard and less mathy to pretty much almost no math, which will be Hugging Face.
Let's have some fun with Hugging Face.
So no other questions before we go to Hugging Face. All right. Oh, look at that. I got my images. Oh, that's great. You guys want a prompt in here? Give me something in the chat. Come on. Someone, give me something. We can generate some more images while we're moving forward. Just so you guys know, these are 100% AI generated images. They are not images that exist out there in the real world at all. This is the mini dolly, so it's not as good as if you were using DALL-E 2, which is available from OpenAI. And this would be an example of text to image, so something I was showing you guys before. Just the word loud. I'll do just the word loud. May have issues.
Delete just the word. It's just the word loud, like one word.
Oh, you just, okay. Loud. Come on, let me in. Let me in. God. Okay, well, we'll revisit this here in a sec. Let me see what they got here. Okay, doesn't look like they're... Come on, here we go. So here's the model. So this is basically... What do you mean no one's downloaded it? So this is basically like GitHub, except for machine learning models. And it's weird to me that they aren't... Is the model not available? The model might not actually be available for download. Maybe it's just for usage. But this is GitHub, except for machine learning models. So people like Google, Facebook, other various companies will do the training. So this took 3 days to train on 8 different, so 8 TPU V3 graphics cards, which are only available via Google's cloud and cost a lot of money. So I'm guessing this was at least like a 3 days on it is probably like a $10,000 to $50,000 run. So if we go here, we can view prices on Google's TPUs. They're V3 TPUs. So this is for V4, V3. Let me see. Here we go. V3, 8 of them. Actually, a lot cheaper than I thought. So you can see here, they ran it on this cluster right here, and it's $8 an hour. So at a minimum, it costs them 24 times 3 times 8. It costs them at least $600 to run that model on the cloud. So you can get access to a $600 model from this guy right here. Except it's not really showing it. But if you go over here to models, you can get a bunch of models for free. And right here for data sets, you can get a bunch of data sets for free that are already, what do you call it? Already, God, why am I blanking on the word? Already
Labeled.
labeled. God, fuck. Sorry about that. So here you can choose categories of different machine learning models you would like. So let's say you want a translation model, and Helsinki is probably the biggest company on here posting their models, and they have fairly good accuracy on their models. So let's say we want to do, let's see, English to, God, who do we have in here? Who's foreign? We got Russian boy. Let me see, English to Russian. So we'll do English to Russian. So right here, Helsinki, English to Russian. A lot of these you can test right away before even downloading them and using them yourself. So this, usually the examples are pre-computed. It looks like this one isn't, but let's see what its output is. Come on, you can do it. I believe in you. There we go. We got some Russian translated output. We can also do our own custom stuff like I like pizza. How about yourself? Then we can go and compute that. If we copy this, we can go to translate on Google and check out accuracy on there. That is, there we go. And it translated to I like pizza. So this, you would need an actual Russian linguist in order to read this to verify how accurate the statement is, because contrary to popular belief, Google Translate kind of sucks. So this statement may be correct, it may not be, I don't know. You can also mess around with the grammar to get different outputs. So this may be more correct now. As you can see, just changing that to a comma will actually give me something closer to what I wanted. So how do we utilize models like this? This is cool and all, but I want to use it. Well, right here, you just click on use in transformers, and this is, this might be a little overwhelming for you guys, especially, showing you how simple that code was before. But we need all this code. I know it's a lot of code, but I promise I can walk you guys through it. All right. First, we got to import transformers. So transformers is made and maintained by Hugging Face. It's a wrapper on top of PyTorch. This is us pulling the pre-trained model, and it's an auto tokenizer styled model. So it's pulling that and loading it up, and giving us the tokenizer. Well, sorry, there's two pieces. There's the tokenizer, which is translation of text into tokens. And then there's the actual machine learning model, which is this bad boy right here. So as you can see, this is pretty complex. We're going to need to pip install transformers. Of course, it doesn't want to install. So pip install Hugging Face. Hugging Face. Did I not spell that right? I thought I did. Oh, I forgot the S. So we'll go ahead and install that. Any questions right now? No questions. So you can deploy immediately to SageMaker if you're using that, or whatever accelerated inference is. And then this will also is a quick button to do auto training. And I believe I think the accelerated inference and auto train is their own platform tools. And then you could also use SageMaker, and it will pre-build all that code for you, which is very convenient. Since we're doing it by hand, we got to do it more manually, which means we need to go through their docs down here, and that will reveal to us what we need to do. So we're using a tokenizer also model. So let's see here. Okay, this was done. Let's go ahead and load this up. Everything's loading up. We're using this type of model. So I'll just copy that name, go over to here, paste it, press enter. All right, here we are. And if we'll stop jumping around, it will usually give us all the docs here on what we can edit, what we can manipulate, what we can get out of it, what are the parameters for it, and also in regards to running it. So there should be some code here in regards to assisting in training and running it. Oh God, this is what happens when you use something live without pre-looking at everything. All right. What the hell? Oh, we need to install sentence piece. Pip install sentence piece. So let's go ahead and go back here. Usually in some of these model cards, they'll have more information on what you want to use. Like I said, there are big companies on here. So if we go to the front, you can see Facebook is posting stuff here, Amazon, Booz Allen, Microsoft, Google, Grammarly. We can go here to Microsoft. They have a bunch of stuff here that's available. ResNet is for image recognition. So we can go here. There's a brief description if you want to try to rebuild it yourself. This has a complete code usage, so we're going to use this since it's going to be a lot easier for our running example than having to do it by default. Auto predicts. Where's the ingest of the photo? Here's the ingest of the photo. So it looks like it comes with a pre-made data set. So if we go here, we'll go ahead and replace these guys with the Microsoft one and rerun. We need the data sets module, pip install data sets. All right, let's see how this goes. It's still importing. Any questions so far?
Oh,
So in regards to the AI aimbot, it was YOLO v5 was taken in the same way. So Torch has something called Torch Hub, and this is not the site for it. These are the docs for it. Here's the site for it. Similar in nature to Hugging Face, where you can scroll through here and find machine learning models that you would like. So I guess there's a new one called YOLO P. Don't know what YOLO P is. It was recently added here, but you can search for different things. So we'll get YOLO v5. And here's where you can grab YOLO v5. There's a pip install. Here's some code right here to get it up and running with a example image and then some stats of the benchmarks of all the various different types of models you can use. And this is for doing object recognition. So you can recognize multiple objects at once. This is YOLO is one of the fastest object recognition models, but fast doesn't always mean accurate, so it may not be the most accurate. Something that is more accurate would be something like Facebook's Detectron. So you can find Detectron in Hugging Face. Let me go to this page. Detectron. Come on, where's the Facebook one? Detectron. All right, I don't know. Facebook's is Detectron. The basic one is usually on here, but you could just search up Detectron 2. There we go. Detectron 2. And this is how you can utilize Facebook's version of it, which is way more robust, way more accurate, and can identify 22,000 different items. It can do image segmentation on those items, just overall object detection, which is the boxes. It can also find skeletons for people. It's very, very intensive, but it is massive, and it requires a lot of compute power to utilize effectively. But it's all pre-trained, ready to use out of the box. You can use it as the default code, or you can fine-tune it on top to get it to do exactly what you would like it to do. So this ran just right now. Let me rerun it because we're getting a lot of, I guess it's good. So right here, this photo from this data set that we just got, it identified that there is a tabby, or also known as a tabby cat, in this photo. So in here, we can do a, we can print the photo with matplotlib. So let me see, matplotlib print photo in Jupyter Notebook. We go in and grab that code for it. Hopefully it's just that easy. And then we can grab this image and just paste it right here. And of course, it doesn't work like that. It wants a path, image open path. Okay, this looks a little better. Image. All right. We'll go ahead and install this. Pip install. All right, I swear I had to restart my computer recently, so a lot of these I have to reinstall because they're no longer on my computer, so this would go faster if I didn't have to restart everything from scratch. Let's rerun this. Is it not done yet? What is going on? Can I just do a print? No, it's not gonna work. Oh, there we go. That's the one I want. And this is gonna be image. I think I need an image show after that. Nope, there we go. So that's the photo that we just analyzed on this data set. So you can see pretty accurate. There's tabby cat. So this is for just overall classification of the photo. So it didn't tell us how many tabby cats there are in here. It's just telling us that there is a tabby cat in here. So that's the difference between image classification and object detection. Classification will give you one classification for the entire image, and object detection will give you the detection of individual objects in a I thought I could just go through these photos. Object detection will give you individual photos inside of the image. Do you guys have any images you would like me to run through this? You can just drop a link in the chat. But you can see as the progression went on, we went from intense math by doing it from scratch to less intense math, more luxurious functional-based coding with Torch, and then now the modern age, which literally Hugging Face only came around in existence, I think like 2-3 years ago. It's very, very new, and it's just now gaining a lot of traction to just using pre-trained models to do what you need to do. A lot of these are state-of-the-art, and you can just fine-tune on top of them. Any questions there in regards to machine learning, the code that we used, Hugging Face, so forth like that? Nothing? No questions.
None that I can think of. Yeah.
All good? I'm all good.
Yeah, Garrett, Blake, you guys better be tracking because you guys are about to do this. So you guys best be prepared for the pain in the brain pain that's coming along, because you guys are going to be doing stuff from scratch for a little bit at first, and then upgrading to using pre-built models.
Yeah.
All right. Well, if no one else has any questions, that will end today's session. I'll linger around for a little bit, mostly because I want to see what it comes out with. The full-blown Dolly you can get from Googling Dolly 2. It's from OpenAI. It's invite only right now, so you can try to get on the you can apply to get on the wait list in order to get access to the actual full-blown application.
Do me and Blake have any assignments due tonight to do for tomorrow?
Say that again.
Do we have any assignments due for tomorrow?
Run the PyTorch code in your Jupyter notebook and just mess around with some stuff, test it a little bit, randomly mess with some of these values in here and see if it makes things worse or better. We'll get into it a little bit more tomorrow.
Good.
Any other questions? You guys are free to leave if you'd like. There we go. That's what it thinks of as loud. It's yelling into a megaphone backwards. It's, ay, ay. Anything else? I'm gonna close this out then if no one else has any other questions.
Or something. Oh, yeah.
Yep, you guys are welcome.
All right.
You
Nice
came,
job.
you came right at the end.
Yep. Yeah, I noticed. Just got out of work, so
Very good.
couldn't really join.
We recorded it. It was kind of rough today, anyways, because I had a bunch of meetings in between it, so we had to take pretty long pauses. We'll probably redo one that's a little better and more hands-on. This was more so because I have interns I needed to give this presentation to at my normal work, so we did it on here so other people could sit in.
All right. Well, I hope you had fun, I guess.
Yeah, man. All right, dude. I'll see you.
Later.